Okay, we're back here today. It's Tuesday. We're back here for second lecture on chapter 30, which is our final chapter in the course. This chapter deals with electromagnetic induction. If you recall from our early chapter, or last chapter, we saw that currents and wires can produce magnetic fields, and we're going to see that in this chapter that changing magnetic fields, or more accurately put, changing magnetic amounts of magnetic field through a loop can induce currents. And this leads into AC power generation and also to electromagnetic waves and a host of other phenomena. So we're going to start off with a mathematical review of a tool called the dot product that we're going to use. And you've done some of this already in 1150 with work. Then we're going to get into this concept called the magnetic flux. And finally, a rule for predicting the direction of a current if this amount of magnetic field or magnetic flux through a loop is changing. This is all related to chapter 30. Specifically, it was sections 3 and 4 today. Homework 12 I'll be posting Friday or Saturday. Remember, you don't need to turn this in. If you did, you wouldn't have time to get it back in time to ask questions before the exam. So I will post the solutions. You should do the homework, study the solutions after you do the homework, and then come into office hours if you have questions. Final exam, remember, is 2 weeks from tomorrow, the Wednesday the 5th. So before we start, we're going to need this tool called the dot product. And the dot product is a way of multiplying two vectors. Now, you can't just multiply them like you can scalars, right? We already saw that when we did this operation called the cross product in the last chapter to get the magnetic field. And here was an example. Remember, the force on a moving charge is Q V cross B, okay? And so you can't just multiply V and B because they're vectors, right? So we had to get the magnitude of this, which is the magnitude of Q times the magnitude of V times the magnitude of B multiplied by Q, and then it's the sine of the angle between them. And then we use the right-hand rule to get the direction of the resulting vector. So the result was a vector whose magnitude depends on the magnitude of the two vectors being, quote, multiplied, and on the angle between them, right? And if they were perpendicular, sine of alpha is 1, and you got the maximum. And if they're parallel, you got 0 because sine of alpha is 0. So the result was a vector. In this chapter, we need a mathematical operation called the dot product. And this one's easier than, you don't have right-hand rules on this one. This one is easier than the cross product, and you've already used it in 1150, but let's do a review here. So suppose you have two vectors, V, and you have a vector W. And they have an angle at theta in between them, okay? And so one way of multiplying these that we're going to use is called the dot product. And what that involves is taking the magnitude of one of the vectors, say V, and multiplying it by the component of the second, W, along the same direction as V. And so what that is V times W cosine of theta. So it's the first vector multiplied by not the second vector, but the component of it along the direction of the first. Okay. And if they're parallel, theta is 0, and then it's just multiplying V times W. And if they're perpendicular, meaning 90 degrees is the angle, cosine of 90 degrees is 0. If they're perpendicular, W has no component along V, and the dot product is 0. So it's the maximum when they're parallel, the minimum 0 when they're perpendicular, and some value in between when the angle is between 0 and 90 degrees. Okay, so this is way easier. There's no right-hand rule, and the result is a scalar. Now, we will show in a minute that if the vectors are expressed in terms of Cartesian coordinates, x, y, z, the dot product's really easy. It involves multiplying their x components plus the product of their y components plus the product of their z components. Okay, so this one's pretty easy to memorize. It's VW cosine of theta, and this is the way to multiply the components. Now we'll show in a minute that how you get this is because if you take the dot product of any of the two unit vectors, like I dotted with I, okay, I dotted with I, the magnitude of each is 1, so it's 1 times cosine of 0, because I and I are in the same direction, which is 1, and so I dotted with I is 1. So two vectors, unit vectors in the same direction, the dot product is 1. And similarly, j dot j is 1 and k dot k is 1. Now, if you have the unit vectors I dotted with j, or I dotted with k, or j dotted with k, they're all perpendicular to one another, right? So their dot product is going to be 0 because cosine of 90 is 0. So let's take the dot product of two vectors, a and b, and we'll write each of them in terms of their x, y, z components. So you got a is ax along the I direction plus ay along the j plus az along the k, and you do it for b. And when you multiply these out, you get ax times bx, and it's I dotted with I, which is 1. And then you have axi dotted with byj, and I dotted with j is 0 because they're perpendicular. And then you can multiply axi dotted with bzk, and I dotted with k is 0, so you're left with only ax bx. And when you distribute out the ay component, you're left with only ay by, and when you distribute out the az component, multiply it out, you're left with only az bz, and this is the dot product written in terms of if you have Cartesian coordinates. You multiply the x components of the two vectors, you multiply the y components, you multiply the z's, and you add them all together. So there's two different ways of calculating the dot product. If you know the angle between them, there's no need to write them all out in Cartesian coordinates. You just you take the cosine of theta and the two magnitudes. If it's hard to get this angle theta in between them, meaning the vectors are written in Cartesian coordinates already, then it's easier to use this way. So you pick the way that's easiest for the given problem. We'll do some examples of this. So we're going to be using this dot product a lot in the chapter. You've already used it in 1150, where you did the force dotted with the displacement. Remember, F dotted with ds. Okay, well, that to calculate work. Okay, so you've done it before, but it may have been a while. So where are we going to use this? Okay, we're going to use this in the calculation of this quantity called the magnetic flux. Okay, and if you remember the previous chapter, Faraday did some experiments, right, where he had a coil of wire, and Faraday postulated that a magnetic field going through the coil would induce a current, just like a current going through the coil induced a magnetic field. And what he found is that if you just held the magnet over the coil, or if you just ran current through the coil and the magnetic field through it didn't change, there was no current. But if you changed the amount of the magnetic field going through the loop, for example, pushing and pulling the magnet up and down changes the magnetic field through the loop, he saw that in that case you got a current. And the direction of the current depended on if the magnet was being pulled in toward the loop or being pushed out of the loop. Okay, so that determined the sign. And so it's these changes in the amount of magnetic field through the loop that cause a current. Not just the magnetic field itself, but the changes. Okay, and so what we need to do next in order to really do anything with this is we need to define mathematically what is the amount, what does that mean by the amount of magnetic field through the loop? And we'll see that it's related to the number of field lines intercepted by the loop. And so if you look here, here's a bar magnet, right? And here's the magnetic field lines of the bar magnet. You have a north pole and you have a south pole. And remember, the field lines come out of the north, they emerge from the north pole and they form loops and they come back in toward the south pole. And the number of field lines is most dense. There's a greatest density of field lines near the poles, and that's because the field is strongest near the poles. And there's a lower density of field lines here away from the magnet and off to the sides because the field is weaker. So the number of field lines is greatest where the field is strongest. So if we're moving this bar magnet up and down through the loop, when the magnet gets close to the loop, the number of field lines through the loop will be greatest, right? Because the field is strongest here, so there's a greatest density of field lines. And when we move the North Pole back away from the magnet, then the number of field lines intercepted by the loop is smaller because we're further away from the magnet, so the field is weaker. So the number of field lines intercepted by the loop, or this flux, must depend on how strong the magnetic field is at the loop, right? So it depends on B. Now the number of field lines intercepted by the loop, or this amount of field, also depends on the area of the loop, right? If you have a bigger loop, you're going to intercept more field lines than if you have a smaller loop. And so this quantity called the magnetic flux must also depend on A. Okay? Now, in addition to B and A, we'll see if we looked at different orientations of the loop that it has to depend on the orientation of the loop with respect to the magnetic field. Okay, so in this case, let's go over to this slide here. You have the magnetic field pointing to the right, and if the loop is perpendicular to the field, oriented perpendicular, you're going to intercept the maximum flux, right? And if the loop is oriented this way, you're not going to intercept any flux. No field lines are going to go through the loop. And when the field is kind of tilted with respect to the field, you're going to get some intermediate amount of field lines through it. And so this flux depends on the strength of the magnetic field at the loop, over the loop. It depends on the area of the loop, and it depends on how the loop is angled tilted with respect to the field. Okay. And so, for example, when the loop is not tilted at all with respect to the field, theta is 0, cosine of 0 is 1, and you get maximum flux. And when the loop is tilted 90 degrees from the field, it intercepts no flux. Cosine of 90 is 0. Okay? So it depends on these three things, the flux. And if we look at the units of B are Tesla, the units of area are meters square, and so flux has these weird units. Teslas times meters square, and just for kicks, they added another unit here. So the product of Tesla times meters square is called the Weber, okay, not to be confused with the grill. And they denote that symbol as WB. So yes, another unit. Ugh. So you can use Webers. If you use Tesla times meter square, I'm not going to hold it against you. That's what it is. So yeah, we have another unit here. So you can see again that if you move the magnet closer to the loop, the field lines are strong. You're going to get more field lines intercepted by the loop. If you make the area bigger, you're going to get more field lines intercepted. And if you tilt the loop so it's flush, so it's oriented facing the field, then you're going to get maximum flux. And we've already done some of this in the last lecture. Remember, you had this motional EMF that was created when you pulled the wire along this direction to the right, and the magnetic field is into the paper, into the screen. What we were doing here, we saw that we induced a current, right? We induced a current in this loop. So the reason was the flux was changing, and it was changing because we were making the area of the loop bigger as we move the loop, as we move this wire to the right, right? This area increased as we move it to the right, and the area would decrease if we were to take this wire and move it to the left. And so as long as we were moving this wire, we were changing the flux, the amount of field lines through the loop, and we were getting a current. And that's why it depended on this speed V, the speed at which we moved it through the loop. And that was called motional EMF. Now we can write this, the flux is defined as the product of the magnetic field strength, B, times the area of the loop, times the angle in between. But if you look back here, that's just the same equation as the dot product of two vectors. In this case, it would be the B dotted with some vector called the area. But area is not a vector, is it? Well, it could be. So we're going to create this vector, since the formula is BA cosine of the angle in between them. We're going to define this, quote, area vector A. Okay, and we all know area is really not a vector, but we're going to define it, one here. And its magnitude is just the area of the loop, and so if it's a square, it's length times width. And the direction is going to be perpendicular to the loop. So this vector we're defining, A, its magnitude is the area, and its direction is just normal or perpendicular to the loop here. And so we can write the flux as the dot product of B dotted with A, okay? And since, remember here, if we look, A is perpendicular to the loop, and so B dotted with A, since they're parallel, cosine of 0 is 0, and it's just BA. And if the loop is perpendicular to the magnetic field, that means the area, here it's perpendicular to the loop, that A is 90 degrees from B, and cosine of 90 is 0, so you get no flux. So we're defining this vector A, which is the area with its direction perpendicular to the loop, and then we can write the flux as B dotted with A. So let's do an example here. So suppose B is along the I direction, the X direction, and its magnitude is 5 teslas, okay? And suppose A is tilted at this angle, and we get its Cartesian coordinates. So the area we would write as 4 meters square along I plus 2 meters square along J. Then the dot product of these two vectors is written as A dotted with B. And when you multiply it out, you get 20, and then I dot I is 1, and then you get 10, but I dot J is 0. And so it's 20 teslas times meter square is the dot product. Now, if you know the angle between A and B, it's usually easier to just do AB cosine of theta. But there are times where it's advantageous, if you don't know the angle, to do it in terms of the dot product. Okay. So let's do another example. So suppose that we know that the magnetic field strength is 0.1 teslas, and we have a loop whose diameter is 2.0 centimeters, and the loop is oriented 60 degrees from the direction of the magnetic field here. So theta is 60. So the loop is tilted 60 degrees with respect to B. Okay, calculate the flux. Now in this case, it makes no sense to write A and B in terms of Cartesian coordinates. We already know the angle between them, and so it's easiest, as it often is, to just use this form where it's B times A times the cosine of 60. And you write for B 0.1 Teslas, and the area, if it's a loop of diameter 2 centimeters, it's pi r square, which is pi times 0.1 meters square. And when you multiply this out, you get a flux of 1.6 times 10 to the negative 5 Teslas times meter square. Okay, so in summary, to get the flux, you can either use this method, which is AB cosine of theta, or you can use this method, which is in terms of the dot product. Okay, and so which one we use depends on which one is easiest for the given problem. Okay, now what if B is not uniform here? What if B is changing through the loop? So here's an example. Here you have a circular loop, and you have the magnetic field going into the page. That's why you see the X's that tail the arrow. So the field is going into the page, but the field lines are closer together over on the right side of the loop because the field is stronger here, and the field lines are weaker over on the left side of the loop because the field is weaker. Okay, here, it's not just as simple as multiplying the two, right? B dotted with A, because B is changing through the loop. So we have to do the mathematical integration throughout the loop. Okay, so we got to do an integral here. Okay, don't worry, in the class we're going to stick with cases where the integrals are pretty easy. Okay, so what we need to do is we need to take the contribution to the flux in each little area. So here's this area here, dA, and the contribution to the flux, d flux, is equal to B dotted with dA. So that's the amount of flux going through this little area. Okay. Then we have to integrate that over the entire loop to get the total flux. And so in general, if the magnetic field is not uniform over the area of the loop, we have to integrate. Okay. If it's uniform, like it was in the previous examples, meaning the direction and the magnitude are constant everywhere over the loop, then we don't need to integrate, and it's just B dot dA. Okay, so there's an example 30.5 in the text, that shows you a case where the field strength is not uniform. So I encourage you to go through that example carefully, and I'll try to find a homework problem also, yippee, so you can work on another case where the field strength is not uniform. So in general, we're going to have to do the integral unless the field is constant over the area of the loop. Okay, so we've talked about how to calculate flux here, right? We take B dotted with dA, and we integrate it, or if it's constant, it's B dot dA. But Faraday observed that it's not the flux through the loop that's inducing a current, but it's the change in the flux, okay? So we're going to have to calculate how the flux is changing. And so there's a law, it's called Lenz's law, which is used to predict the direction of the current in the loop, either clockwise or counterclockwise, corresponding to the change in the increase or decrease in the magnetic flux here. Okay, so here's again, we'll go back to this example. You have a loop, and remember, if you just hold the magnet over the loop and you don't move it, the flux is constant, so you get no current through the loop, right? So suppose that we're pushing the magnet, or we're pulling it toward the loop. So the flux in this case is increasing, right? The field lines coming out of the North Pole here are increasing. We're going to intercept more field lines if we're moving the magnet toward the loop. And so the question that we need to ask is, in what direction you're going to get a current, but in what direction is it? Is it a positive current? In other words, is it counterclockwise, or is it a negative current? And so Lenz's law answers this question. It tells us how to do this. So Lenz's law says that, first of all, that you get a current in the closed loop if and only if the flux is changing. Okay, now, in reality, Faraday discovered this, but Faraday wasn't as good at math, and Lenz was, and so Lenz took Faraday's observations, he put them in mathematical format and got the credit, so that's why you have to know the math. Faraday kind of got screwed there. So Lenz, first of all, just took Faraday's result that you get a current if and only if the flux is changing, okay? Now, the direction of this current is such that the induced magnetic field opposes the change in the flux. So you're like, what does that mean? Well, what that means is that let's do an example. So the magnetic field in this, if you move it toward the loop, is going to increase, right? So, the flux is going to increase. Lenz's law said that you're going to induce a current, right? And a current will create a magnetic field. That magnetic field's direction will be such to avoid any changes in the flux. So if the flux is increasing, the magnetic field induced is going to be in the opposite direction to stop that increase, to oppose it. And so you point your thumb up, meaning the magnetic field will be upward. Since the increasing downward magnetic field, we're going to want an upward magnetic field to oppose that increase. So point your thumb up, and then you curl your fingers along the loop, and that's counterclockwise, and that's the direction of the induced current. Okay, don't worry, we're going to do several examples here. But Lenz's law says that the direction of the field is such to oppose that change in flux. That's the direction of the current. Now, before we get to that, there's three ways again that we can change the flux through the loop, right? We can either move the magnet toward or away from the loop. We can increase the magnetic field strength at the loop. We can change the area of the loop, just like we did with the motional lamp. That'll change the flux, right? We'll have a bigger area, more flux. Or we can change the tilt of the loop with respect to the magnetic field. And this is, in fact, how power is generated in coal-fired power plants. We'll talk about that later. Is you get a coil in the magnetic field, and that rotates, and that changes the angle between the field and the magnets. You got a rotating coil in between some big magnets, and that changes the magnetic flux, and that will induce a big current. So there's three ways to do it. We can increase the magnetic field strength through the loop. We can increase the area through the loop or decrease it. Or we can change the angle. Okay. So let's go back here and go through some examples of applying Lenz's law. Remember, our whole goal here is just to calculate determine which direction this induced current is going to be in. So let's do a few examples. So the first example here, you have a magnet, and here's the North Pole, and we're going to pull the magnet toward the loop. Okay, and remember the first thing you have to do in all of these is determine the direction of the magnetic field. Okay, and if you look at remember the bar magnet, the field lines are coming out of the North Pole, and they're going back toward the South Pole. Here's our bar magnet. Field lines coming out of the North Pole, going into the South Pole. So near the North Pole, the magnetic field lines are downward. So that's always the first step. What direction are these field lines? In this case, they're downward through the loop. Okay. Question number 2, are they increasing or are they decreasing? Well, we're moving the North Pole toward the loop, so the downward flux is increasing. Okay, so that's step number 2. Step number 1 is what direction is this field going through the loop? It's going down through the loop. Question 2, is it increasing or decreasing? It's increasing. Okay, so that means that the amount of downward flux is increasing. So what that tells us is that the loop needs to generate an upward magnetic field to oppose that increasing downward magnetic field. It needs to oppose it because we don't want changes, remember? So what that says is that the loop needs to generate an upward field to oppose the flux. So to do that, point your thumb upward, and then you curl your fingers, and the fingers are curling when you point your thumb upward. The induced field is upward. Your hand curls and counterclockwise, your fingers, and that gives us the direction of the current. It's counterclockwise in the loop. Okay. Now let's do another example. Suppose the North Pole is moving upward, so it's moving away from the loop. Okay, so question 1, what's the field direction? In the loop, it's downward through the loop. Question 2, as we move the loop upward, is this amount of downward flux through the loop increasing or decreasing? Well, we're moving away from the loop, so the amount of downward flux is decreasing. Okay, Lenz's law, remember, says now we can answer the question, what do we need, what does this induced field need to do to oppose the decrease, the change in the flux? Well, it needs to point, the field needs to point, the induced field needs to point in the same direction as the bar magnet to reinforce it, to oppose this decrease in the flux. And so the magnetic field induced needs to point downward. So point your hand downward, and now curl your fingers, and that tells us that the current induced must go in the clockwise direction, right? A clockwise current is what's necessary to get a downward pointing magnetic field. So in this case, the current is clockwise, and you see that the current meter points in the other direction. It's negative. So Lenz's law, here's a summary again of how to do this. Okay? So first of all, always determine the direction of the applied field going through the loop. Okay? And in this case, for the North Pole, remember the field lines are coming out of the North Pole. It's always downward in this case if the North Pole is pointed, the magnet is above the loop. So field is, determine the direction. Determine how it's changing. Okay? Is it increasing, decreasing, or if you're not moving it, it's staying the same. Okay? And then that determines the direction that the magnetic field created by the loop must be in to oppose it. Okay? So if the flux through the loop is increasing, like in this case, the induced magnetic field must point opposite the applied. It must oppose it. If the flux through the loop is decreasing, like in this case, if we're moving the magnet away, flux is decreasing, the induced magnetic field must point in the same direction, which is downward, to oppose the change. And if there's a steady flux, then there's no change in the flux, right? And so there is no induced magnetic field because there's no induced current, okay? And once you determine the direction of the field, you point your thumb in that direction, and you curl your fingers, and that tells you the current. So it's easy once you do this a few times, and I think we're going to do a few examples. If you're already bored and get it, move on. But if you're having trouble a little bit, let's do another example. So suppose, for example, that the field going through the loop, the field is upward. So it's an upward flux through the loop. Okay, and suppose the magnetic field is constant. Okay, well, here there's no change in flux, so you're not going to get any current anyway. So there's no induced current, and therefore there's no induced field, right? If you induce the current through the wire, you're going to induce a field. There is no current, and so there's no induced field because the magnetic field is constant. Okay, now suppose in this case the magnetic field is pointing upward and the flux is increasing. So the magnetic field is increasing. For example, we're moving the North Pole toward the loop. Okay, flux is increasing. That means that the magnetic field induced must be in the opposite direction, downward, to oppose this increase. So the field direction is downward. Point your thumb downward in the direction of the induced field. Curl your right hand, and you get a clockwise current. Here, let's do a third example. Magnetic field is upward, but it's decreasing. So, for example, we have the North Pole down here, but we're moving it away from the loop. Okay? That means that the flux is decreasing through the loop. The upward flux is decreasing. So we need to have induce an upward magnetic field to reinforce it so it doesn't change because it's decreasing. So you point your thumb up, you curl your fingers, and you get a counterclockwise current. Okay. And we can do 3 more examples here, and you'll try these on your own. But again, follow these steps. Always determine the direction of the field through the loop. And then is it increasing, decreasing, or stay the same? If it's increasing, the induced magnetic field must point opposite direction as the applied field. If it's decreasing, the induced magnetic field must point in the same direction as the applied field. So you point your thumb in the proper direction, you curl your fingers, and that gives you the direction of the current. Okay. So let's finish this lecture with an class exercise here. And so let's suppose you have a current carrying wire. So here it is, a long wire, and it's being pulled away from a loop. So the loop is fixed, but we're pulling the wire away. Okay. And so what we need to do before we can determine the direction of the current, that's going to induce a current, right? Because we're pulling the wire away, and the current carrying wire has a magnetic field. And so the amount of field lines intercepting is going to change as we move the wire away. It's going to decrease, right? We're going to have less flux through the loop because we're moving the wire away from the loop, so the field at the loop will be weaker. Okay, so the question is it clockwise or counterclockwise? Okay, so the first thing, as always, we need to do, remember, we need to determine the direction of the magnetic field through the loop. Okay, and go back to chapter 29. To get the direction, we need to first point our thumb along the current. So point your thumb to the left, and then you need to curl your fingers. Remember, the magnetic field lines are circles around the wire. So you need to curl your fingers, and that gives the direction of the magnetic field. And so if you point your thumb to the left and you curl your fingers are coming back around into the screen above the loop. They're out of the screen below the loop, and then they go back into the screen above the loop. So the magnetic field is pointing into the screen. Okay, so that's our first step. Points into the screen. Second step, is it increasing or decreasing as we move the loop away. Well, the field is decreasing at the loop if we move the wire away because the field is weaker. So the flux is pointing into the screen, it's decreasing. That means that the induced magnetic field must also point into the screen in the same direction to oppose that decrease. So the induced magnetic field is into the screen, and if you point your thumb into the screen and you curl your fingers, it means that the field must be clockwise as it goes around the loop. The current. So that you induce a clockwise current if you move the wire away. Now, if you move the wire toward the loop, then this field going into the screen would increase, right? And you would need to have your field induced in the opposite direction to oppose that increase, which means field comes out of the board or out of the screen, and you would get a counterclockwise current. Okay. So practice some of these examples and begin to read sections 30.1 to 30.4 of the text. Here's what you should be able to do after you do that and after you go over the homework problems that are related to this. You should be able to define magnetic flux, including equation, units, and meaning, and you should be able to calculate the magnitude of the flux. If you know the area of the loop, if you know what angle it's tilted at with respect to the field, and if you know how strong the field is, you should be able to calculate flux. Okay? You should be able to do it for uniform magnetic field. Just B dotted with A, or BA cosine of theta. You should also be able to do it if the field is non-uniform. Okay, so that's why you need to go over example 30.5. So you should be able to calculate flux, and then you should be able to state Lenz's law, and you should be able to apply it to determine the direction of the current induced in a loop, clockwise or counterclockwise, if we know which direction the field is in, and if we know whether the flux is changing, increasing, or decreasing. So these two things, there aren't many things to do in this, but you have to work and get good at these, because what we're going into next, where we talk about transformers and inductors, relies on this and on one more concept. So we still haven't calculated how much the change in flux is. Faraday's law is going to give us that. Lenz's law gives us the direction of the current. And so we're going there next. So you're going to have to get good at these. There's not a lot to do, but we need to get good at them. And so that ends today's lecture, and we will see you tomorrow on